Okay, good morning. So this is our 35th lecture. In the previous lecture, we have started our discussion on the velocity potential equation, and particularly we tried to see the main non-linear velocity potential equation, and then with the help of small perturbation theories, which is physically applicable for thin slender objects, actually we have mathematically linearized it. Okay, so similarly, basically when we do the compressible flow analysis, our main interest is to find out the pressure distribution over the surface, because if we know the pressure distribution, then we can actually find out the drag and lift forces. So what we will try to do, we will try to actually make some connection in between the pressure distribution. So the important point is this next topic is linearized pressure coefficient. Okay, so typically if you see the definition of pressure coefficient, it is defined with Cp, and it is typically defined as P minus P infinity, where P is our local pressure and P infinity is actually free stream pressure. P minus P infinity divided by half rho infinity into V infinity square. Okay, so this is the typical definition of a pressure coefficient. So over here, this represents the dynamic head, and this represents the difference of static head at local and free stream conditions. So now, if I take P infinity common, so P infinity will be coming over here, and half of rho infinity V infinity square, and inside I will be getting P by P infinity minus 1. Okay, now what I will do, I will try to multiply this equation with gamma and divide with gamma. So it will be becoming gamma P infinity by dividing also I am by gamma, so gamma by 2 rho infinity into V infinity square and P by P infinity minus 1. Okay, so typically if you see for a calorically perfect gas, this gamma P infinity by rho infinity is nothing but my speed of sound. So all these conditions are corresponding to infinity, so I will be getting this as speed of sound corresponding to the free stream conditions, gamma by 2 V infinity square into P by P infinity minus 1. So from here my Cp comes out to be V infinity square by infinity square will become Mach number, so 2 by gamma m infinity square into P by P infinity minus 1. So this is one of the important equation for linear for pressure coefficient, which is basically used for compressible flow analysis. Okay, so this is the familiar one for compressible flow analysis. Now we will try to find out the value of P by P infinity, and then we will put this assumption of small perturbation theory so that we can find the linearized pressure coefficient. Okay, so typically for an isentropic flow situation, our energy equation is nothing but H plus H infinity plus V infinity square by 2 will be equal to H plus V square by 2. Okay, so now these are the free stream conditions, and these are the local conditions at which we are interested in finding out the values. Now so as we know that this H infinity can be replaced with the Cp into T infinity for calorically perfect gas, and this can be with Cp into T. So ultimately what I will be getting, I will be getting T infinity plus V infinity square minus V square. So from left hand side I am bringing V to this side, minus V square by 2 Cp equal to T. Okay, now this is also known that Cp is nothing but equal to Cp is gamma R by gamma minus 1. Okay, now let's divide this equation throughout by T infinity. So I will be getting T by T infinity is equal to 1 plus V infinity square minus V square upon 2 gamma R T infinity divided by gamma minus 1. Okay, and this comes out to be 1 plus V infinity square minus V square, and this times gamma minus 1 by 2 times of a infinity square, because gamma RT infinity will become a infinity square. Okay. Now, typically we know that what is our local velocity? What is local velocity? Local velocity is nothing but, for using the small perturbation theory, local velocity will be nothing but v infinity plus vx dash square, okay, plus vy dash square plus, okay, so that is my local velocity. Fine. So simply what I will get from here, t by t infinity is equal to 1 plus gamma minus 1 by 2a infinity square into this will become minus 2 v infinity vx dash, v infinity square will cancel, minus vx dash square minus vy dash square minus v z dash square. Okay, is this point clear? So from here I can say that t by t infinity is equal to 1 minus gamma minus 1 by 2a infinity square into, all these terms will become positive. Okay, so now let's also do one thing. I will multiply this term with v infinity square and also divide with this term with v infinity square. Okay, so here v infinity square I have multiplied, then inside if I do divide with v infinity square, then it will be vx dash plus vx dash square plus vy dash square plus vz dash square divided by v infinity square. Okay, up to this point is it clear? Now one important point, because we have already said that vx dash, vy dash and vz dash are small. Okay, so if these are small, then vx dash square by v infinity square comma vy dash square by v infinity square and vz dash square by v infinity square will be very small in comparison to 1. So I can neglect these terms. So ultimately I will get my t by t infinity is equal to 1 minus gamma minus 1 by 2, and this will become m infinity square times 2 vx dash by v infinity. So ultimately 2 is also getting cancelled. So 1 minus gamma minus 1 into m infinity square times vx dash by v infinity. Okay, is this clear? So now if this is my t by t infinity, for isentropic flow I can say that p by p infinity will be equal to t by t infinity times gamma by gamma minus 1. Okay, so now if I do this, then 1 minus gamma minus 1 into m infinity square vx dash by v infinity whole power gamma by gamma minus 1. Okay, now if I apply the binomial expansion, then it will be 1 minus gamma by gamma minus 1 times gamma minus 1 into m infinity square and vx dash upon v infinity. Okay, minus some higher order terms which we will be actually neglecting. Okay, because higher order terms will become v infinity by vx dash by v infinity square, so that we can actually neglect. Is this point clear? So now this gamma minus 1 is getting cancelled, so ultimately my p by p infinity is nothing but equal to 1 minus gamma m infinity square into vx dash by v infinity. And typically you have to remember that whatever the value of p by p infinity we have got, this is nothing but approximate value for small perturbations. Okay, if perturbations are very small, then it will become exact because the magnitude of higher order terms will be neglected. So, but ultimately, this is nothing but the approximate value. This is not the exact value now. Okay. So now I will go back to the definition of Cp. So definition of Cp is 2 by gamma infinity square, gamma m infinity square, and p by p infinity minus 1. So if I do substitute over here, then my Cp will become 2 by gamma m infinity square, and p by p infinity is 1 minus gamma m infinity square into Vx dash by V infinity, and this minus 1 is also there. So 1 will cancel, gamma m infinity square will cancel. Ultimately, I will get Cp is nothing but minus 2 Vx dash by V infinity. Okay. So this we call as nothing but our linearized pressure coefficient. Why we are saying linearized pressure coefficient? Because we have applied over here the small perturbation theory. Okay, so once we have applied small perturbation theory, so this that theory gives us for a typical flow situation, that gives us nothing but the linear form of velocity potential equation. So that's why from that Vx dash component only we are able to find out the value of Cp. So we are calling it as linearized pressure coefficient. Is this point clear? Now we have got all the tools. Our ultimate aim was to find out the value of Cp because we are interested in finding lift, drag forces and movements on the aeroplane because of the fluid which is present outside. Okay, so now let's try to see how we can apply this linearized theory for solving a flow situation. Okay, so what we will do, we will take over here, say the example of a linearized subsonic flow. Okay. So in case of linearized subsonic flow, say I have considered some aerofoil. This is my thin aerofoil, and let's consider this is in the xy coordinate system. Okay. So the profile of aerofoil can be given as, say, y is equal to function of x. Okay. So this is the surface of profile is given y equal to function of x. Okay, so for each x I can find out the, if I know this function I can find out the profile. Now say I am at this point, the streamline which will be passing through this, say that will be having velocity direction something like this. Okay, so say this is the tangent and it is making some angle theta with x direction. So obviously what I will be finding, this component in y direction will be Vy dash and this component of velocity in x direction will be V infinity plus Vx dash. Is this point clear? So I have taken any point on the aerofoil surface, through this I have drawn a tangent and I am saying that this angle theta between the x direction is there. So this V vector will have components. So these components for a 2D two-dimensional system will be Vy dash and V infinity plus Vx dash. Okay, is this point clear? Now from this I can say that tan theta will be equal to Vy dash upon V infinity plus Vx dash. Okay, and what is tan theta? Tan theta is nothing but represent the tangential direction. Okay, so it means it is nothing but the slope of this particular curve. Okay, so if I have this curve y is equal to f of x, anything which is tangent to this will be nothing but will represent the slope of this curve. So ultimately I can say that this is nothing but equal to df by dx, because dy by dx, y is function of x, so I can say that it is nothing but equal to df by dx. So from the geometry itself we have got one boundary condition. Now because we are saying that we are having the small perturbation theory, So for small perturbation theory, what will be happening? Vx dash will be very small in comparison to V infinity. So here Vx dash can be removed, and also I can say that tan theta, for small angles of theta, tan theta will be nearly equal to theta. Okay, so I can say from here that df by dx will be equal to Vy dash by V infinity, because Vx dash is very small in comparison to V infinity, and that is nearly equal to theta. So this is one important boundary condition which actually we have got on the geometry of the aerofoil. Okay. Now for this type of aerofoil, we know our linearized equation. So what is linearized equation? Yesterday only we have derived 1 minus m infinity square into phi xx plus phi yy equal to 0. Okay, for a two-dimensional system. So this is the equation which we derived in the previous lecture. So let's call this entire term 1 minus m infinity square as nothing but beta square. So I can say my equation will be beta square into phi xx plus phi yy equal to 0. Okay, so this is nothing but my governing equation. Now what I will do, I will try to make this equation simpler, more simpler. So I will try to obtain the Poisson form of this equation, sorry, Laplace form of this equation. Okay, so what I will do, let's consider that I am now transferring my physical domain from xy coordinate system to zeta eta coordinate system. Okay, and my transformation variables are zeta equal to x and eta equal to beta times of y. Okay, so now what I am having, I am having some new coordinate system over here, zeta and eta, and aerofoil is over here. The only difference in aerofoil, so all the zeta values are nothing but identical to x values, but all the eta values are multiplied with beta. All the eta values are obtained by multiplying beta with the y values. Okay, so means I will get aerofoil structure over here only, but I will be having changes in this y parameter because this y is getting multiplied with beta. Okay, so this is now my new physical domain in zeta eta system, where my zeta is equal to x and eta equal to beta into y. Now I have to transform my equation from xy plane. So what is my equation? My equation is beta square times phi xx plus phi yy equal to 0. So this is the equation. So now I have to transform this equation from zeta eta plane, sorry, from xy plane to zeta eta plane. Okay, so to do so, what I will do, I will try to first get some tools. So my first tool is del zeta by del x. What will be the value of del zeta by del x? 1. Del zeta by del y, 0. Del eta by del x, 0, and del eta by del y equal to beta. Okay, so now what I am having the value of phi xx, but what I want to calculate, I want to calculate this phi xx in terms of zeta eta plane. Okay, so now let's consider that I have some another function phi bar. I have a function phi bar. Phi bar is nothing but velocity potential function in plane zeta comma eta, and this phi bar is related to my velocity potential function phi in terms of beta times phi of x comma y. Okay, so obviously I will be having some new velocity potential function because I have shifted from this to this. Okay, so ultimately what I want now, I want the relationship in between this and this phi bar, then only I can replace this over here. Okay, so ultimately I can say that my phi in xy plane will be nothing but equal to 1 by beta and 5r in zeta eta plane. Okay. So now if I have to calculate del phi by del x, then that will be 1 by beta, which is constant, del by del x of 5r function of zeta comma eta. Okay. So now I cannot take the direct derivative with x because this is a function of zeta and eta. So what I will do, 1 by beta, I will first do del phi bar by del zeta and then del zeta by del x. Okay. Plus del phi bar by del eta and then del eta by del x. So now what is del phi bar by del zeta? It is say phi bar zeta. Okay, first derivative. So basically del phi by del x will come 1 by beta times of phi bar zeta. This is first derivative. Okay, times what is del zeta by del x? 1. In the previous slide I have calculated. And what is del eta by del x is 0. Okay, so ultimately I am getting phi bar zeta by beta. Similarly, if I calculate del square phi by del x square, which is nothing but phi xx, so that will be equal to del by del x of del phi bar by del x. Okay, what is del phi bar by del x? This sorry 1 by beta times del phi bar by del x. Is this point clear? So it will become 1 by beta into now I have to do del by del x of this term phi bar zeta by eta. So it will be becoming first del phi by del zeta of phi bar zeta by beta into del zeta by del x. Okay, and ultimately I will get nothing but what I will get, phi bar zeta zeta. So double derivative of this, because this was a single derivative, then once again I am doing del by del zeta, so it will be becoming phi double bar of zeta divided by beta square. Is this point clear? Anyone is having any confusion over here? Okay, so similarly I can calculate the value of del phi by del y. So del phi by del y will be 1 by beta times of del phi bar by del y, and that will be equal to 1 by beta times of del phi bar by del zeta into del zeta by del y plus del phi bar by del eta into del eta by del y. Okay, so what is the value of del eta by del x is 0, sorry, del zeta by del y is 0 and del eta by del y is beta. Okay, so first term is becoming 0 plus beta times phi bar of eta. So ultimately my phi sorry, not phi bar, phi y, phi y has become equal to phi bar eta. Fine. Is this point clear? Now what I have to do, I have to take double derivative. So when I will be taking the double derivative, then it will be becoming phi yy, which will become 1 1 by beta into del by del y of, tell me, del by del y of phi bar y, okay, and that will become ultimately 1 by beta into beta times of phi bar eta eta, okay. So ultimately that will be becoming equal to phi bar eta eta equal to, sorry, up to this point is it clear? So now I have calculated phi xx, I have calculated phi yy. So my phi xx is phi bar zeta zeta by beta square, and phi yy is nothing but phi bar eta eta. So if I replace this, then I will be getting beta square times phi bar zeta zeta by beta square plus phi bar eta eta equal to 0. Okay. So ultimately I am getting that phi bar of zeta zeta plus phi bar of eta eta equal to 0. So this is nothing but a Laplace equation. So ultimately what has happened, when we were getting velocity potential equation in the form of pure Laplace equation, can you tell me? If you see the main original velocity potential equation, when we have introduced the assumption of incompressible flow, okay, when we have introduced the assumption of incompressible flow, then our final equation was nothing but the velocity Laplace equation. Okay, so velocity potential equation was in the form of Laplace equation for incompressible flow situation. So over here I have started with the equation beta square phi xx plus phi yy equal to 0, which was applicable for compressible flow in xy plane. Okay, when I have done some transformations and I entered into zeta eta plane, my equation has taken the form of Laplace equation. So it means that whatever the flow phi xy we have in xy plane, and in zeta eta plane I have over here phi bar zeta eta. So I can say that phi in xy plane, because it is governed by beta square where Mach number is being involved. So this is nothing but coming in the form of compressible flow. But in when I have done the transformations to zeta eta plane, the same flow has no involvement of Mach number now. So it means in zeta eta plane this flow has become incompressible. Okay. Now we know that incompressible flow is easy to analyze. So whatever parameters I have analyzed in which plane? Zeta eta plane, these can be then mapped back to the compressible flow plane. Okay, is this point clear? So that is what I am trying to say over here. For same flow over aerofoil, so we are talking about subsonic flow over aerofoil. So for the same situation of subsonic flow over aerofoil, when we are in xy plane, then in our main governing equation, whatever equation we are having for velocity potential function, that is having involvement of the compressible flow. But when we are transferring into zeta eta plane, then that particular equation is not having any involvement of Mach number. So it means it has transformed into nothing but incompressible regime. Okay, so same flow situation in xy plane, which is acting as compressible, same is acting as incompressible in zeta eta plane. So now what I can do, I can basically find out the solution in zeta eta plane, and then I can map back it into the compressible regime, because solution of compressible regime is more complex. So that is something. So whatever this theory we are studying today, this was something which was originated somewhere in 1930s, when people were not even knowing about the shock waves. So at that time they have got this type of thing, that incompressible flow is fully matured. So let's try to get some solution for incompressible flow, and with the help of that, how it can be correlated to compressible flow analysis. Okay, so this was done somewhere in 1930s, and then in the year 1950s onwards, the shock waves and analysis of shock waves etc. becomes prominent. So then people have shifted to different things. Okay, but ultimately this was the original thing when people have initially started analyzing the compressible flow situations. Okay, okay. So now let's try to transform it, how it goes to the velocity potential function. So another important point is, now we have one boundary condition. So what was the boundary condition? If you recall, df by dx is equal to vy by v infinity. Vy dash by v infinity equal to df by dx. So ultimately what I can write, vy dash I can write as nothing but del phi by del y. Okay, so I can say that del phi by del y is v infinity into df by dx. So this was our boundary condition. Okay, so now I know the relation in between del phi by del y in terms of zeta eta. So what I can do, I can say that v infinity into df by dx equal to what I can write over here, del by del y of 1 by beta into phi bar zeta comma eta. Okay, is this one clear? So that will be becoming, or I have just now calculated also, del phi by del y is nothing but equal to phi bar of eta. So what I can simply write, I can simply write it as equal to del phi bar by del eta. Is this one clear? Okay, now say this is equation number 1. Geometrically, if I am in zeta eta plane, if I am in zeta eta plane, say this curvature is given by function eta equal to q of zeta. So I have some function eta equal to q of zeta which gives me this profile. So geometrically, if I take any tangent at this point, then I can say that in this particular plane, say my velocity is vy bar. Okay, so whatever the velocity I was having vy dash in the xy plane, say that velocity in this plane is my vy bar. So vy bar by v infinity over here I can write as nothing but equal to dq by d zeta. The slope of this line will be this curve at this point will be dq by d zeta, and that will be equal to, from the previous case if you relate, that will be equal to nothing but the y component by v infinity. Okay, so from here, this, what is v bar y? V bar y is nothing but the y component of perturbed velocity, and this is in which plane? Zeta eta plane. So if it is in zeta eta plane, then I can write it as del phi bar by del eta. Can I write it del phi bar by del eta? So del phi bar by del eta equal to v infinity times dq by dz. Okay, is this point clear? Now you compare equation number 1 and 2. So here in equation number 1 I have v infinity into df by dx, that is becoming equal to d phi bar by d eta, and here d phi bar by d eta equal to v infinity into dq by d zeta. So from equation number 1 and 2, what I can say that, I can say that my df by dx will be equal to dq by d zeta. Okay, so df by dx will be equal to, what is the meaning of this? The meaning of this is my curvature is having same slope in xy plane and in G theta plane. So it means the shape of the object, whenever we have applied the transformation from xy plane to g theta plane, shape of the object has not changed. Shape of the object has remained same. Only size will be changing because y coordinate is getting multiplied with beta. Okay, so shape of object has remained same. So the meaning is, if I was having aerofoil shape in xy plane, I was having same aerofoil shape in g theta plane. Okay, but difference is that in xy plane I was having it in the form of, compressible flow. In g theta plane, same aerofoil shape is acting as nothing but an incompressible flow. Okay, so now this is something which we have done. Now let's come to the practical aspect. So the practical aspect is, whatever pressure coefficient Cp we have determined, we want to calculate that pressure coefficient uh, in g theta plane. Okay, we want to relate basically. So what was the value of Cp? Minus 2 Vx dash by V infinity. Okay, so if you see, what is Vx dash? Vx dash is nothing but del phi by del x. And del phi by del x, how to relate it in terms of g theta, just now we have seen. What is del phi by del x? Phi bar zeta by beta. So minus 2 by V infinity into phi bar zeta by beta. Okay, so ultimately my Cp is becoming minus 2. What is phi bar zeta? So phi bar zeta is nothing but del phi bar by del zeta, and minus 2 by infinity into 1 by beta. So ultimately it is becoming 1 by beta times of minus 2. What will be del phi by del zeta? It will be nothing but perturbed velocity in zeta plane in x direction, in zeta direction basically. So that perturbed velocity will be nothing but v zeta bar, or say vx bar, because x and zeta are the same, so I can write it even as vx bar. Okay, is this point clear? Del phi bar by del zeta, because phi bar is potential function in zeta plane, so the derivative of this in zeta direction will give me the perturbed velocity. The perturbed velocity I am representing with v bar in zeta plane. Okay, divided by v infinity. What is this? Or let me write it zeta only, then it will be more better to you. What is this term? This entire term. This is identical to pressure coefficient in g theta plane. So I can say that this is some pressure coefficient Cp naught over here. Okay, here this is nothing but the pressure coefficient in zeta eta plane. Is this point clear? So now, whatever the pressure coefficient we are getting in zeta eta plane, this pressure coefficient will be nothing but for incompressible flow situation. So I can say that Cp naught is nothing but my incompressible pressure coefficient. Okay, so this incompressible pressure coefficient Cp will become now Cp naught by beta, which is equal to Cp naught by, what was beta? Square root of 1 minus m infinity square. This is an important relation. So it means in zeta eta plane, it means if you calculate your pressure coefficient for incompressible flow situation, that can be related to pressure coefficient for a compressible flow relation. You have to just multiply with 1 divided by square root of 1 minus m infinity square. This is very famous rule, and it is called as Prandtl Gluert rule. So this is a famous equation which relates pressure coefficient which we have obtained for incompressible flow to a corresponding case of compressible flow. Okay, and this rule is known as Prandtl-Gluert rule. Fine. So what you have to do, you have to simply find out the pressure coefficient for an incompressible flow situation, and that you can simply relate to compressible flow situation. So this is how in the initial days actually analysis of compressible flow has originated. Okay, because incompressible flow was fully matured, so whereas solution for compressible flow was not possible, so this type of analogy was actually, this type of correlation was made. Then the way we have calculated Cp, we have to calculate other coefficients also, drag coefficient, lift coefficient, and the moment coefficient. Okay, so drag coefficient at the moment we don't require, because why? I am talking about over here the subsonic flows. If I consider a subsonic flow, then for inviscid subsonic flow from D'Alembert's paradox, we will be having zero drag force. Is this point clear? What D'Alembert's paradox says, if we are having an inviscid situation and a symmetric object for and we are talking about subsonic flow situation, then we will not be having any drag force over here. Okay, so that is something which we have already seen from the D'Alembert's paradox. So now we will try to relate the lift coefficient and coefficient of movements. So lift coefficient is given by formulation lift force divided by pressure distribution is half rho infinity into V infinity square, and over here in the numerator I am taking force, bottom I am having pressure, so I have to multiply with projected area of the aerofoil in the y plane. So projected area will be say S. Okay, so this is my lift coefficient. Now if I calculate the value of lift, what is lift? So from our very initial lectures, if when I have specifically talked about the lift and drag forces, aerodynamic forces on an aerofoil, so if you remember, lift and drag forces for an inviscid flow situations mainly originate from pressure distribution. Okay, so if we have made the analogy for pressure distribution, and as pressure distribution is not changing, okay, whatever pressure distribution for estimation of Cp we have taken, same is the pressure distribution for estimation of lift force also. So as these forces are originating from the pressure distribution and it is remaining the same, so the way we have calculated this pressure coefficient, in the similar way lift coefficient will also behave for incompressible and compressible flow situation. So I can write CL is equal to CL naught divided by 1 minus m infinity square. Once again, Prandtl-Gluert rule. So if you want, you can do the detailed derivation for this also, but from physical intuition also we can understand, because lift force is originated due to the pressure distribution only. So if the correlation is valid for, if this rule is valid for pressure coefficient, same will be applicable for lift coefficient also. Okay, now similar is the case with movement. So if you have to, so when you are, if you are having say different unbalanced forces on aerofoil, then there will be some movement acting on the aerofoil. So coefficient of movement also I can define as movement divided by half rho infinity V infinity square is pressure, multiplied with S is force. From force also, if I have to get movement, then I have to multiply with distance. So say L is the distance, which is nothing but co-chord of the aerofoil. Okay, so if your aerofoil is something like this, say forces are like this, then some movement will be acting along this chord. So chord length over here is actually L. Is this point clear? So this part is pressure multiplied with projected area is actually our force, and then multiplied with L is our movement. Okay, so similar way I can write Cm is equal to, because you see the denominator is remaining the same in all cases. So pressure distribution, okay, that is remaining the same. So that is the reason I will be calling it as Cm equal to Cm naught by 1 minus m infinity. Is this point clear? So it means if you do analysis for um, incompressible flow using the Prandtl-Gluert rule, you can transform it to compressible flow if you are just knowing the free stream Mach number. Fine. Is this point clear? Now let's try to see the application of this type of theory for some practical situation. So what I will do, I will consider, say I have a wavy profile, something like this, and say this amplitude of the wave is h, and say length of the wave is L. Okay. And another important assumption is h by L is very small then. So it means the amplitude of the wave is small in comparison to its wavelength. If this is the case, then whatever flow will be happening over this, in that flow also I will be having actually small perturbations. Okay. If h by L is large, then perturbations in the flow will be large. In terms of aerofoil, you can see that if your aerofoil is there and it is at small angle of attack, if it is at small angle of attack, then perturbations will be small. But if aerofoil is at very large angle of attack, say this much angle of attack, then our perturbations will be large. So it means that whatever analysis I presented for aerofoil case in the previous slides, that analysis is applicable only for small angles of attack, because if you go for large angle of attack in aerofoil, then our perturbed velocity values will be actually large in magnitude. If these are large in magnitude, then this linearized theory of small perturbations cannot be applied. Okay. So similar is the case for this wavy profile also. We are assuming that our our wave amplitude is small in comparison to wavelength. So whatever the flow perturbations will be existing, these will be actually small in magnitude. Okay. Is this point clear? Now we know that our equation for what is the equation for this? Equation for this is in xy plane, because I am dealing only with the xy plane. So in xy plane, the equation is 1 minus m infinity square into phi xx plus phi yy is equal to 0. Okay, so that is the equation. So whenever I have this type of equation, I can, a linear equation, I can easily solve this equation by the method of separation of variables. Have you studied conduction and radiation course? So in that course, method of separation of variable might have been used a lot. Maybe in your course on convective heat transfer also, for some problems, method of separation of variables might have been used. Okay. So what we do in case of this method, if my phi is function of x comma y, I will be assuming it equal to f of x, some function which is sole function of f, and then g of y. Okay, this is called as method of separation of variables. So phi is a function which is depending upon x and y, but I have a function f which is a sole function of x, and it is, phi is nothing but product of two functions which are sole functions of x and y. This is called as method of separation of variables. When we do the multi-dimension conduction problems or even transient conduction problems, then actually this method is popularly used. Okay. So now okay, if this is the case, then if I have to calculate del phi by del x, what it will be? It will be del f by df by dx into g of y. Okay, If I have to calculate del square phi by del x square, then d square f by into. Similarly, if you have to calculate del square phi by del y square, that will be becoming f of x into dy square. So now you can replace these two terms over here. Okay. So our original equation is 1 minus m infinity square into del square phi by del x square plus del square phi by equal to 0. This is our original equation. Okay. So now what I can do, I can write 1 minus m infinity square into, here it will be becoming d square f by dx square plus d square g by dy square. Here it will be function of x, here it will be g of y equal to 0. Okay. So if I rearrange the terms, I can get I can get 1 by f of x into d square f of x by dx square plus one by g of y into 1 by 1 minus m infinity square into d square g of y by dy square equal to 0. Okay, so if we just do the small rearrangement, then we will get something like this. Now let's say if I fix x, that I am not varying x, if I vary only y, in that case what will be happening? My first term will be obtained at a particular value of x, so this value will be constant. If I am fixing x to a particular point in the flow field, so for that particular point, the function which is sole derivative having sole involvement of x, that will be nothing but a constant, and in that case I will be finding that this y will also be constant, because from this equation, if I am at particular value of x, what is the meaning of this? If I am at particular value of x, I have this first derivative fixed. Okay, but ultimately from this equation, if this is constant, then this entire term will also be minus of that constant. Is this one clear? So this entire term will be equal to minus of that constant. So ultimately I will be finding that at this x along the y direction also this second term will be actually constant. Point is clear? So that is the reason what I can say. I can say that if my 1 by f of x d square f of x by dx square is some constant minus k square, then my second term 1 by g of y into 1 by 1 minus m infinity square into d square g of y by dy square will be equal to k square. Now what are these? This is one ODE, this is another ODE. So I can easily find out the solution of these two ODEs. So the solution of this ODE will give me f of x, solution of this ODE will give me g of y, and ultimately what is my phi xy? F of x into g of y. Is this one clear? So now these are very direct equations, so their solution also we have many times seen. So if you see, the solution of g of y comes out to be a1 times exponential of minus k into square root of 1 minus m infinity square y plus a2 times e of k square root of 1 minus m infinity square into y. So a1 and a2 are actually constants of integration. Similarly, what will be the value of f of x? F of x will be, say, b1 into sine kx plus b2 into cos kx. If you solve these two equations, then these are the solutions. Okay. Now I have some constants over here. So these constants can be obtained from the boundary conditions. So what are the boundary conditions? First boundary condition is that when y is large, okay, y is large, y is going to infinity, then my velocity or gradient of phi has to be finite. Is this point clear? Because when I will be moving far away from the wall, so I will be getting a constant velocity value over there. Okay, so corresponding to that, I must get a finite value of gradient of phi. Okay, then another point is if I calculate slope at wall. Okay, so dyw by dx, that is nothing but my slope at wall. So slope at wall will be equal to v yw dash, component of perturbation velocity in y direction, divided by v infinity plus vxw dash from our previous theory. Okay, slope of the curve will be equal to y component by x component of the velocity. So by making this assumption of vx dash is very small in comparison to v infinity, I will be getting this, and this will ultimately be 1 by v infinity into vy dash I can write as del phi by del y when calculated at wall. Okay, so when my h by l is very small than 1, okay, if h by l is very, amplitude of the wave is very small than 1, then I can say that my wall is almost at y equal to 0. Okay, so I can make this assumption that del phi by del y at wall can be calculated at nearly equal to del phi by del y at y equal to 0. Okay, and now what I can do, I can substitute these two boundary conditions for both function equation of y and equation of x, and then I can get the values of all the constants. I am not showing that complete procedure because this is just the substitution of the boundary conditions. So ultimately if I do so, I will get a final equation of phi in terms of x and y equal to v infinity into h divided by square root of 1 minus m infinity square and exponential of minus 2 pi into square root of 1 minus m infinity square into y by L into sine of 2 pi x by L. So this is the solution of phi which you will be getting. So what I have done now, I have shown you that how our linearized perturbation theory actually makes our problem very simple. So I am not going into detailed boundary condition because this is something which you have studied earlier in your many courses. So you can try it by your own. If you are finding difficulty, you can ask me. Okay, method of separation of variables is many times you have studied earlier. Okay, so this is the value of phi. If this is the value of phi, then I can calculate now vx dash. Vx dash will be component of velocity in perturbed velocity in x direction, and that will be equal to del phi by del x. So I can take the x derivative of this. So if you do so, you will get v infinity h by 1 minus m infinity square into exponential of minus, sorry, not exponential because derivative we are taking, so exponential will also come, but 2 pi by L cos of 2 pi x by L. Anyone is having class? You can leave. Into exponential of minus 2 pi square root of 1 minus m infinity square y divided by L. So this is the value of Vx dash. If I have the value of Vx dash, I can calculate my pressure coefficient. What is the value of pressure coefficient? Minus 2 Vx dash by V infinity. So you simply do it. You will be able to get the value of Cp. And if you want to calculate value of so you can substitute and then obtain. If you want to calculate the value of Cp at wall, what we will be doing? We will be calculating this minus 2 Vx dash by V infinity at y equal to 0. So that value, if you want to calculate, that comes out to be minus 4 pi by square root of 1 minus m infinity square into h by L cos of 2 pi x by L. Is this point clear? So simply what we have done, we are having a wavy structure. Over that wavy structure we were able to estimate the value of phi. If phi I am having, I can estimate all velocities, and if I can estimate the velocity, I can estimate the coefficient of pressure. Okay, important point is that from this coefficient of pressure you can see, if this is your wave profile, then what will be the corresponding pressure profile? Corresponding, say this is my wave profile. So corresponding pressure profile will be at a phase of 180 degrees. Why? Can you tell me from this? Why? So this will be my pressure profile at phase of, because here I am having a negative sign over here. Okay, so this can be given with the cosine curve, and this is coming with minus of cosine curve. So it means I will be having pressure profile just opposite to that of the our given profile. Okay, so the point which is above, there I will be having highest value of the pressure, and at peak I will be having lowest value of pressure. Okay. Sorry, pressure profile will be just opposite. So now let's try to see that what is the effect of Mach number on this. Okay, so if you see, one simple observation we can make, that phi is inversely proportional to 1 by square root of 1 minus m infinity square into exponential of minus 2 pi into square root of 1 minus m infinity square y divided by L. So the meaning is, if your m infinity is large, then exponential of this term will become, this is exponential of minus. So this, if m infinity is large, then exponential term will become 0. 1 by infinity is equal to 0. Is this point clear? So this will make the value of phi as, this will make the value of phi as 0. So when your sorry, when your y is large, because if m infinity is large, then this is something. So first let me do, when y is large means, say y is approaching to infinity. So when y is approaching to infinity, so this term will be 0, and so phi will be tending to 0. Okay, phi will be tending to 0. If you just want to calculate at wall y is equal to 0, so Cp at wall will be simply becoming inversely proportional to square root of 1 minus m infinity square. Okay. Another interesting fact is, because phi is inversely proportional to m infinity square, so if your m infinity is very small, then phi is large, but if m infinity is increasing, then value of phi will keep on growing small. Ultimate point is that if you have some situation like this, this is your wavy structure and this is your same wavy structure. Okay, but here if m infinity is very smaller than 1, and say here m infinity is in the range where this up to the range up to which this solution is applicable. So this solution is applicable only up to subsonic regime. So say m infinity is nearly equal to 0.8. So physically what you will be finding, you will be finding that if your flow was reaching somewhere over here disturbance free, in this case it will take more time to become more spatial coordinate to become disturbance free. So it means that if you are increasing the Mach number, that will keep on increasing the region in Y up to which its influence will be felt. Is this point clear? So when your Mach number is small, then influence of this object in the Y will be up to lesser distance, and if our Mach number is large, then influence of this up to the uh, in the y direction will be actually more. So up to more portion we will be feeling the influence of this. Okay. Now another one final thing I want to just conclude. So we have seen this rule that Cp is equal to Cp naught by square root of 1 minus m infinity square. So this was our Prandtl-Glauert rule. Now this Prandtl-Glauert rule was having certain certain deviations from the experimental data. When it was compared, it was giving actually under predictions. Okay, so many people have actually later on tried to modify the correlation relations for Cp. So one such relation was given by Lewton. So his argument was that when we are making analogy, we are only considering the free stream Mach number, but actually pressure distribution we are considering over the body. Okay, so when we are considering the pressure distribution over the body, then what should happen? Our local Mach number should be considered to make the analogy. So what he has done, he proposed that Cp must be equal to Cp naught by 1 minus m square. Okay, and when for isentropic flow situation the relationship between m and m infinity is obtained, then this relation can be given as Cp equal to Cp naught by 1 minus m infinity square root plus m infinity square into 1 plus gamma minus 1 by 2 m infinity square divided by 2 1 minus m infinity square and Cp naught. So this m is related in terms of m infinity for an isentropic flow situation, then we get this particular expression. And the beauty of this expression is that when my value of Cp naught becomes very small, approaching to 0. When Cp naught is approaching to 0, then this relation comes out to be Cp naught by square root of 1 minus m infinity square, because this second part will become 0. So ultimately this comes back to nothing but Prandtl-Glauert rule. So it means that for the situations which are very close to incompressible flow situation, okay, because for incompressible flow situation our Cp naught will be small, because when you are increasing the Cp naught at Cp at wall is inversely proportional to 1 minus m infinity square. So if you keep on increasing the Mach number, then this value will keep on increasing, and at m infinity equal to 1, even this will become infinite. But m infinity equal to 1 is not a physical condition possible for this analysis, because this analysis is not applicable for transonic flow. It is applicable only for pure subsonic flow, which is up to Mach number of 0.8. Okay, so ultimate point is that when Cp naught is 0, it means our flow situation is very close to the incompressible flow situation. Then Prandtl-Glauert rule gives the this Lewton's formulation becomes Prandtl-Glauert rule. So it means it gives accurate prediction for that point. One another rule was given by this Karman and Tyson. So what they have done, they have basically uh, they have given the relationship as Cp equal to Cp naught by 1 minus m infinity square. So their rule is more accurate because they have solved the non-linear perturbation equation using the hodograph method. So there is one hodograph method with the help of which we can even solve the non-linear perturbation equation. So Karman and Tyson has actually solved the non-linear equation using the hodograph method, and they have obtained Cp equal to Cp naught by 1 minus m infinity square plus m infinity square divided by 1 plus square root of 1 minus m infinity square times Cp naught by 2. Okay, and now if you make the comparison in between the three rules, so say this is Cp, this is m infinity, so here say I am having values minus 1.8, minus 1.0, say somewhere over here minus 0.2, and this m infinity must vary from 0 to 0.8 because we are talking about subsonic flows. Okay, so say this is the equation as per Layton rule, then this is the equation from Karman and Tyson rule, and say this is the equation from Prandtl Glouet rule. So if you now plot over this the experimental data points are something like this. One is here, then here, then here, so like this. So you can see that Karman and Tyson is mostly fitting in the entire region, whereas Layton and Prandtl are actually fitting in the very initial portion when situation is very close to the incompressible flow situation. Okay, so the actual graph to the actual scale values you can refer to in your textbook. Okay, so it is in chapter number 9, figure number 9.8. So there you can refer the actual graph as per the scale. Fine. Okay, so this is all about subsonic flows. So now we will